For those who doesn't know me, my name is Felipe Yosida. I'm responsible to support Stellantis here in the town. I have some contacts here, like Eric Martin, Jugis, and so on. And I really appreciate everybody. My sound is terrible. Sorry about that. I guess it's my connection. But I just want to thank you everybody to join us, and I let Eduardo to proceed with the presentation. Okay.
Okay, thank you, Felipe. Good morning, everyone. Welcome to another webinar organized by OpenCAD. My name is Eduardo Lima. I am product marketing engineer here at OpenCAD. Well, today we brought a special speaker to talk about AUTOSAR, exclusively to Stellantis. Sweta Bradavati is graduated from Tufts University with a master's degree in engineering management, and the Manipal University with a master's degree in automotive embedded systems. She is a senior product manager at Mafrox, focused on AUTOSAR, DDS, and the Simulink code generation products. At Mafrox, he works with the developer and the field to help drive products, hold maps, develop the product positioning strategy, the go-to-market process for new products, and the workflow-based demos and videos. You have a panel of questions that will be answered at the end of the webinar, okay? So, Sweta, welcome to OpenCAD webinar, and thank you for supporting this event. I'm sure your presentation will be very helpful for this team. To all, enjoy it, and thank you.
Yeah, thank you, Eduardo, and thanks for the introduction. So I don't have to say anything more. He covered it all. I'm excited to be here to present the latest and greatest support of AUTOSAR Classic and Adaptive from Simulink, especially. We proudly call it as model-based design. Before I dive into this presentation, so I have like an agenda. So I have split between AUTOSAR Classic and Adaptive. I'm just interested to know like how many of you are interested in AUTOSAR Classic or Adaptive. Can you help me understand that by commenting in the chat? Like, do you prefer Classic or Adaptive, or you want both? So I'll evenly split my time based on the interest I see in the chat window.
People, don't be shy.
Yeah.
It's important to us to understand, right? Because of course the main point would be the presentation of AUTOSAR Adaptative, but this kind of quiz or question, I would say, is great for us to understand how deep, I guess, you can understand about the AUTOSAR Classic. Okay.
Yeah. Yeah.
I guess people are shy somehow.
All right, maybe you can type in as we go with the slides. So let me go ahead and start with the overview of AUTOSAR before I dive into either Classic or Adaptive in general. Okay. So as you know, the automotive industry has witnessed an exponential growth in the complexity of the both software and hardware components in a car. As we all know, there will be hundreds of ECUs in a car to make it a safe, secure, and smart vehicle. So all the intelligence and vehicle functions are not implemented by a single ECU, but there will be a separate ECU for powertrain, airbags, lighting control, and etc. These features are implemented on different ECUs by different suppliers, and the way each of them are implemented are dependent. So if you use a non-AUTOSAR architecture, The software and hardware pieces are tightly integrated, which would be hard to reuse. So the AUTOSAR organization came up with this AUTOSAR layered architecture, and which is now, like in past 5 years, it is popularly called as AUTOSAR Classic. As you see, it has 3 layers on top of the microcontroller hardware. The top layer has application software related implementation within a self-contained units called software components. And then there is in the middle, there is runtime environment that provides a communication abstraction for application software, and the basic software layer, which provides ECU abstractions, communication abstraction, microcontroller abstractions, and services, including memory diagnostics, and so forth. This modularity can help to manage the growing complexity of automotive systems that provide flexibility to upgrade or update the product. It also makes it scalable across product lines. So today you can have AUTOSAR and non-AUTOSAR ECUs in a car which is already on the road. Then the modeling of ECU software is an important part of developing your algorithm. So with Simulink, you can easily model and simulate as well as generate C code uh, with embedded coder. So now we have seen that Classic is already on the road and is successful. And so what are the main motivations for introducing another platform like AUTOSAR Adaptive? So that the main drivers are automated driving applications, which are demanding and they need more power, more computing power, more communication power, and also yeah, and it need to be easily updatable. So the AUTOSAR organization introduced this adaptive platform based on POSIX operating systems, and that has service-oriented communication implemented in C++. The application can also be easily updatable. So yeah, um, and in the auto world, we are witnessing an intense focus on how we stay connected with the outside world when we are behind the wheel, automated driving over the air update. To support this rapidly changing application, the AUTOSAR organization has introduced a new platform called AUTOSAR Adaptive. That is based on POSIX operating system and service-oriented communication, and the implementation is all done in C++. So it can be dynamically updatable, and that can link services and clients and adaptive at runtime. So this adaptive AUTOSAR will continue to coexist with the classic AUTOSAR platform. And in a near future, autonomous and highly connected car, we can have both AUTOSAR Classic and Adaptive ECUs. And MathWorks is an active participant in the development of both Classic and Adaptive standard um, organization, and we heavily involved in those meetings, which happens monthly, quarterly, as well as yearly. And we have engineers just dedicated with this development of the standard, which brings in the perspective of how model-based design um, can be helped with the development of AUTOSAR Classic and Adaptive. So AUTOSAR is much more than an architecture. It consists of core partners, including OEMs. These 9 companies, which are called core partners, have brought together their respective areas of expertise to define an automotive open system uh, architecture standard to support the needs of future in-car applications. And then have over 57 premium partners. So I recently attended the AUTOSAR Open Conference and noticed this member list is growing, and the total is more than 320 members as of last week. As you can see here, MathWorks is one of the premium partner, and also and there are AUTOSAR as associate development partners as well. So I mentioned AUTOSAR Classic is already on the road. The good news is AUTOSAR Classic, which is developed using MBD, is already on the road by using MathWorks solution. So we are providing AUTOSAR support from past 10 years for production purposes. And on this slide, I have compiled some interesting technical articles and presentations from our customers. The first one I would like to highlight FCA, which is now called as Stellantis. They have used our solution, and in one of the MathWorks Automotive conferences, they described their complete development processes from requirements to modeling and code generation in Simulink up to in-vehicle testing for AUTOSAR software. And BMW, which is one of the founding member of the AUTOSAR consortia, talks about using MBD and AUTOSAR in an agile workflow with continuous integration. So John Deere is not really an automotive company, and it is an agricultural vehicle manufacturer. So they have provided an interesting talk about how they use AUTOSAR and MBD to deal with the challenges of complex agricultural machinery. Then LG Chem and Magneti Marelli have discussed developing AUTOSAR software in the context of compliance with ISO 262 and ASPICE. Then finally, Idneo, it's a Spain-based company and that provides a different perspective of using MathWorks AUTOSAR toolchain for development of complex device drivers. And they have reported that the 70% faster development time and discovered 80% of errors in the design phase instead of in hardware testing. And this is all about classic user stories. And we do have a user article on AUTOSAR Adaptive. So that's from Electropet, and they have used our solution for developing AUTOSAR Adaptive software for driver monitoring system um, um, that follows AUTOSAR Adaptive standard. And they did mention that MBD could accelerate development of end-to-end AUTOSAR Adaptive software systems. So you saw the overview of bit about how non-AUTOSAR, classic, and adaptive. I just want to dive a deep into this. So in the classic side, the components, the software components, it's a self-contained units, and those are contains the implementation of application algorithm. So, but they are static software, and that is done at design time, which follows signal-based communication that has hardware abstraction that would make it monolithic update. That means it will allow only full image flashing. Whereas in adaptive, that allow dynamic service discovery at runtime, and that follows service-oriented communication, and it allow higher hardware abstraction, which will make it more flexible to go for selective updates like over-the-air update, as there is a new changes that makes it easy to push the updates. All right, this is like a really high level view. And now I'm switching to how this AUTOSAR architecture maps to generic ECU software. So I have a generic ECU, and in the topmost layer is the AUTOSAR software component that has an implementation of application software, right? And it is the most important structural element present within this AUTOSAR architecture. And this AUTOSAR software components can have ports that interact with the outside world. And then the implementation is done using the virtual function bus that interconnects the different application software components and handles the information exchange between them. So then by using this virtual function bus, the application software components do not need to know with which other application software components they need to communicate. And the software components give their output to the virtual function bus, which guides the information to the imports of the software components that need the information. This is possible due to the standardized interface of the software components, which specifies the input and output ports as well as the format of the data exchange. Then the RTE, the runtime environment, implements the virtual function bus, that's VFP functionality on an ECU. These AUTOSAR software components are connected to another software component via well-defined connection points called ports. So here the ports are categorized depending on the direction. That would be like provide or require port, sender or receiver ports is a type of port where a sender distributes information to one or more several receivers. Then there is this client server ports. The server is a provider and the client is a user of a service. The client initiates the communication requesting that the server performance service, transferring a parameter set if necessary. The server waits for incoming communication requests from a client that performs the requested service and dispatches a response to the client's request. So, for example, this server can be your diagnostics server, can have multiple clients. So, for example, my client AUTOSAR software component is calculating the average vehicle speed. When the overspeed occurs, then the server diagnostics software will set the diagnostics error. Then the application output is plugged to the hardware pin, which will control actual application on car related probably body control module, powertrain, safety, or so forth. Now I have a real example, which is exterior lighting ECU. Here you see that there are implementation of left turn lights, control of the left turn or right turn lights, brake lights, and the blinker algorithm. So here the right turn or left turn lights needs to be turned on, or you want that to be blinking at a certain intermittent speed, then you get the data from the blinker algorithm. And if there is a brake is applied, right, that's a sporadic event, right? And that's communication is happening client or server. So that's why these kind of ports are used. And if there is any diagnostic error occurs, like an overspeed error, then again we will use this client server type ports. And once once the algorithm is processed and when there is a signal has to be sent on or off, then it is done via an API that goes via basic software and then connect to a hardware pin and then finally to the actual load on a car. So this is a really high level example. Like the lot more technical specification goes into the implementation, but I simplified it to help you understand how this really the software architecture works at a high level. So all this while I talked a lot about AUTOSAR software components, right? And it's composed by one or more runnable entities. So that means that represents the internal behavior. So an AUTOSAR software component, for example, the brake lights algorithm can have multiple runnables that implements the functionality, and it can have sender or receiver port or client server ports depending on your application implementation. So then these runnables, so say we talked about application software component that is in an application layer. Inside that there are multiple runnables. So each runnables should have at least one event attached. Here it is nothing but allocating to an OS task. All runnable entities of a software component are not necessarily allocated with a single OS task. And the scheduling of runnable entities is defined during the configuration of RTE. So the logic of scheduling of each runnable needs to be created by the user. And there are several RTE events defined by the AUTOSAR standard, and we support all these events. So there is something called timing event. So that is intended for periodically scheduled runnables. So when you want your runnable need to be executed periodically, then I would attach that runnable with this timing event that is available in Simulink UI. And there is this data received event, so are intended to trigger the runnable when data is received. Then there is mode switch events are intended for runnables that should be triggered either on entry point or exit, or on exit, or on transition between entry or exit. So for example, if your odometer value is saved to NVRAM when ECU state changes from run to sleep mode. So here the ECU state manager state is changing, right? So we want to trigger that particular runnable when this mode switch really happens. So then you would attach the runnable with this mode switch event. The next one is operation invoked event. So that can be a client server type event. The example I gave you about the diagnostics event manager, right? If you want to set a diagnostics, then the client would ask and the server will be served. So when an operation for server ports is invoked, then this operation invoked event can be used or attached to the particular runnable. Yeah, and then this init event. So the AUTOSAR introduced this AUTOSAR initialization event. You can use an init event to designate an runnable as an initialization runnable. So if you don't designate a runnable, like in Simulink, it will create a runnable initialization runnable by default. If you don't want to use that initialization runnable, then you can assign a particular runnable as your initialization runnable by using this init RTE event. Then there is data received error event. This runnable entity is activated automatically by the RTE whenever error is detected on a data or a receiver port. Then the RTE raises a data received error event when the communication layer reports an error in data reception by the receiver component. All right, and then the last one we support is the external trigger occurred event that service signals an external triggered actor event to another component. The receiving component activates a runnable in response to an event. So yeah, we support all these events, and the logic of scheduling of each runnable needs to be created by the user as per the application. All right. So I talked about AUTOSAR Classic and Adaptive and also non-AUTOSAR. So there are multiple standards here, right? The good news is with Simulink, you can design your software once. So that could be a non-AUTOSAR AUTOSAR, which is potential legacy ECU, and that can be deployed to many software architectures targets and by following multiple standards. The important point about this is the developers can start from the legacy model and configure it for either classic or adaptive instead of starting from scratch every time. You can also migrate their existing components to new architectures by reusing existing workflows. So with Simulink, you can design, simulate, and deploy the models to legacy ECU, to an AUTOSAR classic or adaptive application, and also to FPGAs or GPUs for demanding applications such as motor control or autonomous driving. So this brings to an end of the introduction part. Do I have any questions coming in? Let me take a pause and look for it.
So far in the chat, we didn't have any question, but I would say that in general basis, it was an important information because perhaps in the team, I don't know if everybody from Stellantis here is already using the AUTOSAR block set per se, or even working directly with some AUTOSAR standard. But in general basis, I guess it was important for you to highlight mainly this slide. I mean, it is important to understand the legacy ECUs. I don't know if this is a question from my side. Okay, Shweta. It is somehow I don't know if the word is interchangeable, or can I set my design to AUTOSAR Classic and then change it to Adaptative or vice versa? I don't know if it's a right question for you, but in this journey to become AUTOSAR Adaptative, or to go through the AUTOSAR Adaptative, you have the Classic first, right? So is there any kind of situation where we can back to the Classic? I don't know. Is it possible?
It is possible to interoperable between multiple standards. That's the whole message with MBD.
Okay.
You can go from any architecture to other architecture. Yeah.
Perfect. Thank you. Thank you.
All right. So let me dive into MathWorks solution for Classic. So here I have a zoomed in representation of Classic architecture. So with our tools, you can model and generate C code for the top level layer. And we do, it is also interoperable with third-party authoring tools if there is an ARXML created from there, and you can import that into Simulink. Or you can also model architecture model right in Simulink, or you can import an architecture in the form of an ARXML from third-party tool, and also switch back between a Simulink model and an architecture model. I'll show that in my upcoming example. So, and also you can simulate the interaction between the application layer and the NVRAM, diagnostics, or FIM. And this is only for the verification purposes. All right. Now, how do I map or convert a non-AUTOSAR model to an AUTOSAR model, or you can also do for Classic to Adaptive as well. But here I'll show you how you can convert a non-AUTOSAR to an AUTOSAR model. You can do that by using a quick start tool that will automatically map non-AUTOSAR entities to AUTOSAR properties. So here I have a legacy model. It's a simple model. I'm converting that into AUTOSAR, launching an AUTOSAR component quick start, and it has changed the target from ERT to AUTOSAR. And here you can choose the AUTOSAR component type, or you can model reference from the AUTOSAR software component model. So I would like to create defaults based on the Simulink model, or you can import an ARXML into Simulink. So here I'm just converting it. All right, so this tool has automatically mapped the Simulink imports to AUTOSAR ports. And these are the runnables you see here, and these are all periodic runnables. These are the imports, and that has AUTOSAR data access mode ports and data elements. And these are the out ports mapping to Simulink AUTOSAR ports, and you can see the corresponding communication attributes. And in the AUTOSAR data dictionary, you can see how all the ports, Simulink ports map to AUTOSAR, and these are the runnables. I talked about initialization runnables and other runnables, and these are the events. You can choose the RT events based on your algorithms. The interrunnable variables is a connection between two runnables, and these are the data elements. And over here in the XML options, you can go ahead and choose how you want to generate code and also the XML. So let me launch the code generation settings. Notice that the AUTOSAR.tlc is chosen. You can choose the schema version. And the latest one we support is 1911 for Classic and also for Adaptive. 2011 is on the way. Oh, it's already released. Yeah. Yeah, once the configuration is done, you can generate code. Yeah. So here I have opened an in-canvas code view. You can see the corresponding links to code and the model. It's an initialization runnable. Yeah, that maps to initialization block. And the corresponding XML files are generated with the schema version. We chose 4.3.2. All right, and in this way, you can convert a non-AUTOSAR model to an AUTOSAR model. All right, and this is a design workflow I'd like to highlight. Customer, I mean, you can start from an Simulink model or from an architecture model as well, and then generate code and export your XML like you just saw in the demo. That's called bottom-up workflow. In the top-down workflow, you start from an architecture that could be from your third-party tool, export an ARXML from that tool, and import that into Simulink platform, either as an architecture model or a Simulink skeleton model, and then implement your logic, then generate code. And this is called top-down workflow. The combination of this is round-tripping. Yeah. I'm just curious to know, what workflow do you use in your current projects? Do you mind typing up in the chat, or feel free to unmute yourself and share your workflow?
I guess people are a little bit shy, but we do have a question, Shweta, but I guess we can answer that when you enter into the AUTOSAR Adaptative, okay?
Okay, cool. Okay, and you can furthermore do SIL and PIL as well. So Delphi Technologies used our tools for authoring software architectures right in Simulink for their multi-core powertrain, electric powertrain ECU software. Yeah, and they have linked to the requirements, and they did architecture all the way till code generation. So next I have a demo of authoring AUTOSAR compositions. The AUTOSAR compositions is nothing but aggregation of multiple software components. So how do we create AUTOSAR architectures in Simulink? So that's the demo I'm going to demonstrate now. So here I have several controller modules and throttle sensor Simulink models. I would like to build a throttle sensor model. For that, I have learned using a template, software architecture template. Let me, yeah, over here you have options to create a model or link to a model or import from XML. And in this palette, you can access components, compositions, and also diagnostic services like NVM, basic services like NVM and diagnostics from this panel. Yeah, and here is it's a purpose-built composition editor. It provides a view of AUTOSAR software architecture based on the virtual function bus. So let me clear this default content from the window so that I can construct a new compositions since we have a bunch of sensor components. Let me create a subcomposition architecture for sensors. And yeah, it's a composition inside a composition. Let me call it a sensors, and inside the sensors, we add a component and call it a TPS primary. Notice there is an option right here to create model from this component or link to a model. Since we already have a Simulink model, we'll probably link it, or create component model from an XML. Okay, let me link to the model because since we have an implementation done in Simulink already. Yeah, and notice that the badge has changed, indicating that it's a sensor actuator component type model, component type. Similarly, I'll add other components for secondary sensor and also monitor and pedal sensor and so forth. And then connecting them up. And yeah, the composition editor uses all the great things you like about Simulink Intuitive editing capabilities. So let me update the model to flush out any integration issues. All good to go here. We'll now save our model, call it my TPC composition, and notice that you use the same extension as any regular Simulink model. Now that we have created our composition, I will show you the integration with requirements, that's Simulink requirements. For that, let me open the requirements manager app. It opens the requirements tab. We can open requirement set. It contains 4 of the throttle position control application components. To link an AUTOSAR component to a requirement, we can drag the requirement from the browser to the component block. Yeah. All right, you can see, can drag. Now the natural next step in the workflow is to apply V&V by simulating the composition. So for that, we will turn on function connectors to visualize the function calls that the component models may be calling. Look at that. The throttle sensor model calls into demand NVM service functions over here. To simulate them, let me add the reference implementation for both diagnostic, because I see diagnostic calls as well, diagnostic service component and NVS service component blocks. Let's update the model again to make right connections. Look at that, because since there were calls, and it shows there's a connection. And over here, we can configure the IDs for the client ports. Now I would like to connect these to test harness, the throttle body plant and pedal to verify my algorithm is working as per my requirement. So I'm doing a model reference to the my TPC composition model. And connected the inputs and outputs. And now I'm enabling the scheduled rates and then opening up this and then enabling schedule editor option so that I can view the execution order. I can change the order as per my requirement and see how it would work now by running this model, like for simulation. Yeah, I can visualize the control. The input is very close to the output. It looks cool. Now the next step is to generate code and ARXML. And for that, I have choose a folder. Yeah, and the model is running. Since we have 6 components, it's building component one by one. So with composition, one is usually dealing with a number of components, and therefore we'll have a number of generated artifacts. So we have made it easy for you to collect all these artifacts, so you are ready with the next step in the workflow, which is likely to integrate with the RT environment. And we create a .zip file which contains all these files. We are almost done with building. Okay. Now let's examine the generated .zip file. Notice there are 2 subfolders, ARXML and source, and each has a component as component and implementation description files. In this ARXML folder, you can find description files for composition and also for individual components. And in the source file, you'll find C code for each software components or composition components. So composition is just merely an architecture thing. In the C code, you just get the code for individual components. So there is an example to try this on your own. It's part of the documentation. I would definitely encourage you to do that. All right, so in the example, we started from bottom up. We created Simulink model. Vice versa, you can also do top down. You can import hierarchical compositions in the form of an AirXML right into the architecture model. And there is an example for that as well. I have added a link over here. So the top down, I have an example of top down workflow here. This is an composition AirXML representing using the schema 4.2.2. Yeah, you can import that using this APIs as well, or you can do it manually as well in the UI. Yeah. So here I'm using import option. Using the importer app, I'm just browsing for composition or XML file. Yeah, you can furthermore configure modeling options. Yeah, it is importing all the components of the compositions. Yeah, so you can see all the components over here. And then similar to the previous demo, you can add the logic here and then change the schema if you want. It was for 4.2, you can change it to other schemas as well, then generate code. And right now it's just a skeleton model. You can add the logic for the model. All right. So this is a old one until 21AB, but until 22A, we have support for 2011. And we do support timing extensions, and it's important because there are several runnables, right? And that will have hundreds of tasks and maps to multiple cores. And it's important to have map runnables to tasks and to cores. And therefore, AUTOSAR introduces timing extensions to provide timing requirements that guide the construction of the system. So here I have example of execution order, like the timing extension defines what should be the execution order is, and you saw sort of that in the demo. I'll show you the importance of that here. Like how do you know what order you have evaluated or simulated this model, right? It is hard to tell with data dependency. Let me try to figure out how this would affect. Here, output of the runnable one is connected to a scope to check the results. If you run runnable R1 before R2, you would get a graph in the first graph. And if you swap the order, you'll get a second graph, and you can see the results are being changed. That definitely impact your algorithm execution. So in order to support that, as you saw in the demo, we allow you to import an AirXML that consists of timing information that will be reflected in the architecture model, and view that in the schedule editor. They've changed that order, and that will be restored in the exported AirXML as well. This is just a demo of that, of the execution order. I'm just changing it. And I'm just making sure once I make the changes, it is still following the AUTOSAR rules. And now I'm generating code. So look out for timing extension information in the AirXML along with the code. I mean, it's not really reflected much in the code. It's all the information you see is in the AirXML. That will be helpful when you go down the further tool chain of your development when you go beyond model-based design. Yeah, and here you can see what runnables are run in a particular order. All right. Furthermore, you can create ECU extract from an architecture model, which is an important information which contains the configuration description needed for a specific ECU. So you can import as well as export such information within architecture as well as Simulink model as well. So we do support AUTOSAR library routines, like includes math subroutines like interpolation, algorithms for curve, map, pre-lookup. You just drag and drop these blocks and you'll get an optimized code on code generation. And also it will point to that implementation. And to summarize with AUTOSAR Classic, you can model and simulate both the classic application software, and it is help you to adapt multiple design workflows for import, update, and export description files, including the extensions. And then you can author software compositions and System Composer. That's an authoring tool. You can, as you saw in the demo, you can import and export the composition XML files as well. Finally, is the C code generation that is can be optimized and used for production. So AUTOSAR block set is available on every stage of the development cycle. So it can be from your requirements too, right? I mean, you saw integration with Simulink requirements and also managing of AirXML file. And then you saw the simulation, which helps you understand the interaction between your application as well as the BSW services using the blocks. And also you can have integration with Simulink test as well, and then generate C code. Furthermore, you can do SIL and PIL for verification purposes and also use Simulink test for verification. And finally, you can generate code and AirXML for the deployment purposes. So then using AUTOSAR block set and embedded code, you can generate code for applications up to ACLD, and then IEC CertKit helps you streamline your ISO 26262 development processes because it contains the mapping between the tables in ISO and the corresponding MBD. All right, that's all about AUTOSAR Classic. Now I'm switching to AUTOSAR Adaptive. So the layers of Adaptive are similar to Classic in that there are components, runtime, basic services, and hardware, right? So perhaps the biggest difference between Classic and Adaptive is that applications call the public interface of the foundation or service directly, so that API service area is much larger. And then it is useful to note that the Adaptive is not necessarily running on bare metal, but it could be running on a virtual machine, and also talking to a virtual Classic machine as well. So I'm just laying out how this is mapping the layers of Classic, no, layers of AUTOSAR Adaptive is mapping to Classic terminologies. So even here, MathWorks tools are used for modeling and C++ code generation of adaptive applications. So I'm going to go through some of the key concepts for adaptive. So the key concept one, the OS provides multi-process POSIX OS capabilities. And each adaptive application is an independent OS process with its own main function, logical memory space, as well as namespace. And also, if you look at the process management, the OS also provides process scheduling. The execution manager provides process lifecycle management, starting, running, terminating processes. And the communication manager provides inter-process communication. So both these two models are akin to the RTE in Classic. Then the key concept two, the use of service-oriented inter-process communication. If you look at the IPC between processes, this IPC can be local via the communication manager or over a network, again via the communication manager. So if you look at the type of communication, Classic as sender and receiver or client server, right? In Adaptive has service-oriented communication, which can be broken down into methods. It is more like function calls, and then communicate events. It's think more of like a message-based communication, and the fields, it's think more like a data. Yeah, and then adaptive. So in Simulink, you can model both events and methods as of now, and we do have plans to support fields in the near future because many customers are asking for it. The key concept three is that everything is C++. All modules and applications need to be written in C++. So if you look at the adaptive roadmap, and it was introduced in 2018, and MathWorks started to support that from 2019 itself. And these customers are some of the and this sorry, I'll back up a bit. So this is the roadmap I said, like we are now into the fourth version of the standard, and the latest one is already sixth version, 2111. And these and we have been supporting all that, and we started to support the adaptive standard from 2019. So over the next few slides, I'll take those adaptive concepts and show how you can model and generate code in Simulink. So this adaptive application has required ports, which are typed by a service interface, as we discussed. Service interfaces have events, methods, and fields, right? So in Simulink, an adaptive application would map to a model. A required port events would map to a messages in Simulink. Here I'm converting a messages to a signal using shipping order sublock set example. So on the provided port, that is very similar. Again, adaptive application map to a model, and event would map to an output. Similar to that, it can have client server port where it can map the methods to Simulink function calls, subsystem, and also function call ports. So, and the adaptive workflow is very similar to classic workflow. You can start modeling your algorithm in Simulink, then generate C++ code and ARXML, that's bottom up. Or you can start from an architecture model, export that ARXML and import that into Simulink, that's top down, and you can also perform round tripping. Let's see AUTOSAR adaptive in action. So here I have an ARXML. And I would like to import that into Simulink. I'm importing that using these APIs. Notice that it has created a skeleton model with inputs and outputs. Right, and now we need to add the logic. So with this approach, all the adaptive application related information is already taken care, and you can see the mapping is already done. Yeah. And you can have this as a one-time discovery or dynamically discover your application. That's the beauty of the adaptive standard. Yeah, and that's a provide port, and here I'm just modeling events. And over here, you can choose the XML options. All right, and notice that we are using AUTOSAR_adaptive.tlc instead of just AUTOSAR TLC. You can choose a schema, and the latest one is 2011. I already have a lane guidance algorithm over here. I can just insert it. Yeah, connected all the ports, and yeah. All right, now it's time to generate code. You can see ARA.com calls, and it's all C++, and the corresponding XML files can be found here. All right, so yeah, you saw how to import an adaptive model in Simulink. You can do vice versa as well. You can convert classic model to adaptive or adaptive to classic as well. All right. Yeah, then furthermore, you can configure your model to generate ASAP2 or A12 file generation, and the file versions we support are highlighted in the UI. You can choose to exclude comments upon A12 file generation as well. So then we do support ARA-COMPER. That's a persistency that offers mechanisms to adaptive applications to store information in the non-volatile memory of a machine. The data is available over boot and ignition cycles. Yeah, so and you can generate C++ code for processing persistency, and you can import and export the AR XML that describing this persistency ports and interfaces. So in terms of deployment, you can create Linux executables for runtime calibration. You can run the executable as a standalone application as well. And this adaptive Linux executable toolchain provides adaptive functional libraries for code generations. And we do support runtime logging for adaptive executables that will allow forward event logging information to a file console or network as defined by the AUTOSAR diagnostic log and trace specification. So in the release 22A, we do support DDS binding that will allow the communication between adaptive applications. This feature is supported out of the box with the Linux executable toolchain. To summarize, you can model and simulate as well as test the adaptive software that will allow with event as well as method communication and then dynamic service discovery. And we do support import, export adaptive XML files as well. Then generate optimized C++ code for production purposes. We do have several shipping examples to try on your own. I would definitely encourage you to do that. And then for more information, I encourage you to visit AUTOSAR Blogs page on mathworks.com. So that's all I have for today, and thank you for your attention. Now I'll open up for questions.
Thank you. Thank you, Shura, for your presentation. Actually, we do have a question from Wasila. I can read for you. What is today available in Networks package to support adaptative AUTOSAR targets? For instance, code generation with embedded coder.
Yeah, so the example what you saw We do support C++ production quality code generation for Adaptive. I mean, with embedded code, yes, it's possible. The demo what you saw, it's with the AUTOSAR adaptive target using embedded coder. Does that answer your question?
He mentioned yes.
Okay,
Thank
cool.
you. I guess people are a little bit shy today, but we don't have any further question. In the end of the day, from my perspective, Shweta, it was important to share this topic because people are really engaging into that for the future of Stellantis, as I understood. So few people, let's say it's not a few people, but today they are already using the AUTOSAR block set. But as the account manager for Stellantis Latam, my target would be to understand a little bit more how deep they want to understand both of the teams, both of the issues, right? Both AUTOSAR Classic and of course the Adaptative. Please, everybody, if you do have some questions, let us know because we have an opportunity to talk to the product manager here. So it will be perfect for you guys to really ask your questions because we have her time at least for more 10 minutes.
Hey, Philip, this is Julia here.
Yeah, thank you.
I was trying. Hey, I was trying to find the way to turn on the microphone, but I guess that I had to raise my hand, right?
Okay, go ahead, Julia.
Okay.
Thank you.
Yeah, no, I just wanted to thank you for the webinar and your time and also Shweta time to present it to us. I think it's really important for our team in Stellantis, and I think that the information that was presented and the all the details and the differences between AUTOSAR Classic and Adaptive, they're really good and really welcome. So thank you for that. No question, but just wanted to acknowledge that.
Yeah, thank you for acknowledging me, and feel free to reach out to me if you have any questions after the meeting. That's fine too.
Okay.
Yeah, I'll make the slides
Okay,
available
thank you so much.
for you. Yeah.
Okay. Thank you.
This is one of the topics that I would ask you, Shweta, to share with us this presentation.
Yeah,
and of course, you guys, as the face of OpenCAD and MathWorks for you guys from Brazil, my cell phone is always available, and of course my contact as well. So please let us know everything that you want to really dig into everything that Shweta has presented to us today, so we can actually request her any kind of further questions of everything that she actually presented to us today. Okay, so thank you for this acknowledge, Julia.
Okay.
Thank you so much.
Thank you. Sounds good. Thank you.
Okay. You're welcome.
I guess we don't have any more questions, Shweta, so I just want to wrap up here. Shweta, thank you so much for your time. I know that Eduardo will, of course, make the wrap up for the marketing side as well. But from my side, as the account manager for Stellantis, I really appreciate your time and to share your knowledge about these two topics, which is really important to Stellantis. And people from Stellantis, we have some material that we have shared with you. This material was provided by Shweta, some links, 2 links that Eduardo has shared with you. And of course,
Yes.
the material that is like a handout to you that you can download here into the panel. So let us know if you have any trouble to download it, okay? Again, thank you everybody. Thank you, Shweta, for your time again.
Yeah.
And Eduardo, please you can follow.
Okay. Yes. If there are any more questions, I'd like to thank the presence of the Stellantis. Yeah. As Felipe said, and Sweta, thank you very much to explain for us. I think that Stellantis can apply AUTOSAR more now. Oh, so we are finished this webinar. So have a nice week for that all. Thank you, guys.
Bye. Thank you.
Bye,
Bye-bye.
bye, guys. Thank you so much.